Okay. All right. Good morning. My name is Bill Chu. I'm a professor at the University of North Carolina, Charlotte, and my student Jing is and I are gonna be here talking about secure programming support in IDE. We're at OWASP, so we all know software vulnerabilities is a big issue. Developers needs to learn more, but our focus is a little bit more. It's going to be really focused on how to prevent errors by developers, and we all know that even the most experienced developers do make mistakes. So from our perspective, that today's tool support for secure programming has really primarily focused on static analysis and dynamic analysis, which for the most part works like old compilers, where you run your analysis, you diagnose the problem, and you fix the problem. So they tend to be very reactive. So what we wanted to look at is how to proactively support programmers avoiding mistakes in the first place, as opposed to fixing them retroactively. And by doing so, we want to include the developers in the security loop. So we started out by researching literature on previous work in terms of studies on why people make mistakes in programming, not just security mistakes, but programmers make bugs all the time. We all have debugged. And really, many of you probably know Donald Knuth, which is like one of the fathers of computer science. And he actually did a self-study on his own substantial programming activities and found out that mistake of omission is one of the largest class of mistakes. It's not like he doesn't know, he just forgets to do things because there's so many things you have to worry about when you're programming. So that's an interesting insight for us. We also have done some study by interviewing professional developers, specifically in the context of secure programming, why people make security programming mistakes. And what we found, interestingly, is there's a disconnect between conceptual understanding. Many of the programmers we interview, professional programmers, understand security, understand secure programming. That's important. I think that's sinking in. But they don't necessarily connect that context with what they're doing here. They often rely on, for example, some framework or process going to take care of security for me. Even for something basic as input validation, they tend to focus more on the functional aspects and the business logic as opposed to from a security perspective. So our approach is sort of based on the assumption that many common software vulnerabilities are caused by mistake of omission. So for example, failure to perform input validation or output filtering, just people forget. Failure to check security invariants before performing critical operations, for example, CSRF, broken access control. It's not they don't know, they just forget. And so what we want to do is we want to interactively identify those common security mistakes, issues, and using reliable heuristics and warn the programmers in IDE, pop up a warning and say, here's something you need to pay attention to, and we provide them with options to actually take actions. And specifically, we've identified two types of actions. One is what we call interactive code refactoring, and the other one is interactive code annotation. And I will give you a demo of the first type, or the prototype we implemented, and we'll talk about the design for the second one later on in the talk. So the design rationale is the whole tool is based on this idea of recognition instead of recalling. The idea is programmers have very heavy cognitive burdens. We want to help them to recognize problems as opposed to think about it cognitively, and using this key human-computer interaction principle. We want to take full advantages of developers' application knowledge. They are programming in the context, they know the business logic, they know the application context, and we want to support secure software development best practices. For example, we've embedded OWASP ISAPI into our plugin so people can generate code, use ISAPI, latest version of ISAPI to validate their inputs or encode their variables. And we want this to be policy driven, so none of this is hardwired into the program itself so that it can be changed to different environments. So the demo we're going to have is we call it ASIDE, stands for Application Security in IDE. It's based on Eclipse Java. And basically have the feature that's fully implemented is code refactoring. So I'm going to turn it over to Jing. She's going to show you a demo.
All right, so So our site approach aims to provide developers secure programming practice support during the program construction. And our demo comes with a Savvy validator and encoder as an example of such practices. And here's how a site works. Once the site is installed as a plugin to Eclipse, you can run it against a project by right-clicking on the project's name in the Explorer view, Project Explorer view, and then navigate to a site menu. So based on the preference setting of a site, which can be viewed through Eclipse preference dialog, a site will identify vulnerable code in the project source code using predefined rules. So as you can see here, the default aside rule setting uses the default trust boundaries from the plugin aside. But these rules can be extended for at your will, as you would see later. So right now, if I click OK, and so to make eSavvy more easily available to developers, a site actually does eSavvy configurations automatically the very first time you run a site. And these configurations include copying the eSavvy libraries into the lib folder under the project, and also putting those libraries onto the project's class path, and also generating copies of all the configuration files of eSavvy. And then once the site finds a match in the source code, it will mark the code with a warning and also highlight the code. As you can see here in this transaction servlet, there are 4 parameters that retrieve the string from HTTP request through the method invocation get parameter, and this is actually a common source for untrusted inputs. This aside warns you immediately after invoking this function in your code. So if you delete the function or the statement, the warning will go away. But aside doesn't just stop here. If you hover over the highlighted code or click on the warning, you will get a, I'm not sure whether you can see it. So you will get this explanation view, as well as a list of input types that are coded in the eSavvy properties files and validation files. So through this explanation view, you'll get an idea of what the problem is. For instance, why the code is vulnerable, and what consequences you may have if you don't take care of them, and well, how can you go approach and fix the problem. So if you want to roll out of your own solutions, no problem. You can go ahead and write your own code to address the warning. And Aside doesn't stop you from doing that. But Aside can also provide you the code generation mechanism to generate code for you to deal with, to address the warning. And it's very easy. All you need to do is to select an appropriate input type from this list and just click on that. So for instance, for this stock name variable, I'll just go ahead and choose, say, zip string. And this is a rule from eSavvy. And if I click on that, a segment of code will be generated, and this code actually employs eSavvy's validator's getValid input API to validate this stock name. And this code, generate code, is just like the other code, which is subject to modification. You can put your own exception handling code here. And as you may notice that after I Upon my selection of one of the solutions from the list, this warning disappears. So if I undo this process, the warning will show up again. Sometimes untrusted inputs are encapsulated in some sort of composite data type, such as data structure, rather than a primitive data type, such as string. So it's only reasonable it's only reasonable to warn developers when the untrusted input gets extracted from the data structure, and that's how a site does it. So, for instance, this request.getParameter map is a very good example. So we first, let me see, comment use these instead of the invocations of getParameter to retrieve the parameters from the HTTP request. Since a site's default trust boundary policy do not cover request.getParameter map this method invocation, so you need to extend the default rules to add your own ones. So to that end, all you need to do is to right click on the project and you go navigate to aside, and then you add aside rules. Aside will create a folder named aside rules under your project, and all the rules are written in XML, and this trust boundaries.xml file is where you need to put the rules in. So for the sake of time, I've already prepared the rules for get parameter map. So just copy this, paste in, and save it. And then all you need to do is to tell aside that you want to use the rules that you just created by going to the preference setting, and then you say, okay, I want to use trust boundaries from the project under detection, and then you click OK, and then aside responds to the change by identifying vulnerable code by using both the default policies and also the extended ones that you just created. And now you can see that the method invocation map.get are marked as vulnerable because it's where you get the untrusted input. So this code is actually similar to the ones we saw for get parameter. If you delete them, the warnings will go away, and also if you hover over, you will get a list of input types as well as actually here. See, you will see the explanation view. And instead, besides input validation, ASAT also supports output encoding by identifying, places where the application content gets output to software like web browsers. Here's an example at this line that the application variable part out is rendered to a web browser, which is a very common indicator of process scripting vulnerability. So when you hover over or click on the icon, you will get a list of encoding strategies from a SAPI. And if you, for instance, for this case, I will choose HTML encoding, and then the code will be generated. The encoding code will be generated to address the warning. So besides input validation and output encoding, we also ASAT also provides a feature what we call secure coding on-demand service. So it's for variables or untrusted inputs that are not identified by ASAT automatically because of all kinds of reasons, for instance, lacking trust boundary rules. So for cases like that, all you need to do is to select, for instance, this one, you just select this variable and then right click, and you will see in the context menu, you will see a menu items that is SAPI validator, and then the sub menu items are the rules that can be extracted from a SABI for your validation. For instance, I'm going to choose safe string. So, and this will generate the same code routines that does the validation. And this is all I have for the demo.
Okay. Thank you. All right, so as you can see, that so we putting the programmer support. So the idea is we want to make it as easy as possible for the developers to do the right thing. Okay, and sort of in our work we identify there's at least two different strategies for doing input validation. One strategy is you perform input validation right before a critical operation, like you're putting stuff into the database. Or writing things to the browser HTTP stream. The advantage of that approach is you know exactly what you're doing because this is the last chance you can validate or encode something. The disadvantage is you may have to do redundant validations. For example, you get one input and it goes into two different database tables and then you get two different warnings, as I'm sure many of you have seen those in warnings generated by say something like Fortify. And then and also you may fail to validate because it may be difficult to foresee all the critical operations. Today this set of operations is critical and then tomorrow maybe something else is, and then this strategy is going to not be able to catch that. The alternative strategy is you validate something as soon as it comes in, and then you say, well, no matter where it goes, then I know what the input is, right? The advantage of that approach is you have developers' attention right then and there, make the right choice. But the disadvantage is it can lead to some false positive because some things may never go anywhere, and then you ask for validation anyways. And then it sometimes does not work well with dependency injections, some of these things, because you don't know where the input is coming from. So a site really can handle both strategies, all right? So, and we have experimented with different versions looking at different things, and we've done some evaluations of a site for the refactoring part against an open source project using Fortify as our benchmark, and the details are in the paper, which I will give you a link later on you can look at. But just to summarize, just to give you some additional ideas. So once you have this, then this is not currently fully implemented, but this I think is a very good idea that shows that this input validation is very different from the current, say for example, filter-based input validation, because you're closer to the application context. You're not doing it outside of your application, before you hit the for example, semantic validation. So once you, let's say for example, identify an input variable as a file path, okay, then you can have an option to say maybe limit it to a particular directory, right? So as an example, that you can have a lot more semantics that's specific for the application, and you can add more security protection for that. So I just want to point that one out. And as I said, we've evaluated this against Apache Rolla, which is a full-fledged blog server. With 65K lines of code, more than 65,000 lines of code, and we did a simple Google search on powered by Apache Rolla, and then 1.8 million entries came up. So there's a lot of things out there that use this as a tool, and then as a platform, and then we benchmarked against Fortify SCA. And then the result is published in a paper which is referenced. I'll give you a link to this. You can get that. And John is not here, but one of the co-authors of that paper is John Melton. Is one of the project leads at App Sensor project. So John actually did a benchmark using his company. He was working at that time for a large financial service company as a software security auditor, and he used his company's best practice as a benchmark to analyze Rolla using Fortify, and then we benchmarked the results of that against a site and see what sort of results we get. And in the interest of time, I do want to cover some of the more sort of interesting research ideas. So I'm going to skip some of these things. This is what Fortify found. And the thing I want to take away is vast majority of the errors that Fortify generated for this Apache Aurora are input validation, output encoding kinds of stuff. And by the way, John thought that program was average quality. It's not particularly good, but it's not certainly bad. He's seen much worse than that. So vast majority of them, probably more than about close to 60% of the problems are those input validation and output encoding errors. And 90% of those ASIDE could just take care of right away. So in other words, if you use ASIDE, you could have solved all these problems before you hit static analysis. All these things will be done. Incidentally, there was a university challenge yesterday. Our team, we fielded a team from UNC Charlotte. We won the defense part. Unfortunately, we didn't win the overall competition, but we won the defense part, and the judges were arguing which part is more important. So I'll let this to other people. But the interesting thing is we actually used ASIDE against two web applications they wanted us to defend. And ASIDE found like more than 30 vulnerabilities, and we used this mechanism, we're talking about that, to just very quickly wipe out those sort of low-hanging fruits. So I think ASIDE is particularly effective sort of handling these kinds of things as its current prototype implementation just can take care of these things very, very quickly. But I do want to talk a little bit about false positives. So we did some false positive analysis. So ASIDE reported more than 118 taint sources that, because our current, this version, we track taint sources. More than 118 taint sources than Fortify did. Okay? But we did sort of analysis on all these cases. We find that 94 of them are what we would determine as potentially exploitable. And you can make a very strong argument, and we do, as a best defense in-depth practice. You should validate them anyways. There are, however, 24 false positives. So I'll give you an example of something that we think is a good thing to do as a defense in-depth strategy. I would like to hear your take on it. Here's a snippet of code where there's an error, an exception was thrown, and as a parameter to the exception handling routine, the code has request.getURL. All right. Now this URL could have a JavaScript in it, and in this particular case, Fortify did not flag it because I suppose this URL didn't go anywhere, or this exception handling didn't do anything. But this could be, be the entry point for something like log poisoning. So we think this is a good practice, especially when there's very little overhead. You just click and generate some HTML encode code that would sort of prevent those kinds of things from happening as your software evolves. And, but it does have some false positives as the 24 cases. So for example, in this case, the code reads in a parameter, and that parameter is either going to be true or false. It's a Boolean test. So in all likelihood, this is probably harmless. You don't have to worry about it. But because we handle taint sources, we'll flag that as well. So there are some false positives. So just to quickly summarize the portion of code refactoring, and specifically within the context of the demo, is we're trying to address validation and coding issues at the time of development. Requires no specialized training. We do not assume developers know static analysis or anything like that. Everything is in situ, in the browser, in IDE. We want to be able to best capture application context. Want to save time fixing vulnerabilities that may be found as opposed to coming back to fix it later, as in most current best practices. And that we find it to be very effective. Vast majority of those errors we could actually detect and save. And we can save quite a bit of time in terms of, in terms of workload for the auditors. So for example, about 1,000 out of 3,400 warnings Fortify would generate, we could have taken care of at the development time. So some practical implications for ASIDE. We believe that a tool like that can be a very good complement to static analysis. So you can generate, for example, you can generate cleansing rules. That's one of the big problems for weeding out warnings from static analysis is, how do you know that something has already been cleansed? One of the things that SI can do, because the developer has taken certain actions, you can generate some cleansing rules, and that could be as an input to your security auditing people and say, oh, somebody has already done that, so I don't have to worry about it. Okay, so I think that could be a value add, and it could also be used as sort of a light version of static analysis, taking care of some of the basic vulnerabilities without having to invest in a full-blown static analysis, and I think that is also of value. So now I have, in the next few minutes, I'm going to talk about some of the issues. I think we want to take this idea of supporting IDE a little bit further and looking at some more interesting vulnerabilities, and this is, stepping more in the research domain. We have not fully implemented that there. So again, going back to our premise, what we're trying to do is to remind developers of potential security issues and encourage them to take some actions. So the second mechanism that we're going to talk about is called interactive code annotation. And I want to first off by saying that annotation is not a new idea, but the way we are using annotation in this context is different from traditional annotation, because traditional annotation are text-based. You write certain sort of extra syntax program statements essentially in the program, right? So the kinds of annotation we're talking about, the interactive annotation, first of all, it's not text-based. The focus is not about asserting something about a piece of code, but to talk about security relationships between different parts of the code, which is very different from the traditional annotation, which just talks about locally what this piece of code does. And it's entirely, we envision it to be entirely point-click based, so no extra syntax or anything like that is needed. So this is what we're talking about. Because we find this is, people often misinterpret when they see annotation. Oh, developers don't like to do annotation. And we wanted to make it really easy and hopefully that there is value add, as I will show you later on. So let me give you a motivating example, sort of a simple, very simple online banking kind of example. So if you have a username, role, first name, last name, you have accounts, have account number, transactions, you have transaction IDs that are tied to particular accounts, and then you have a relationship between account number and username, right? So it's sort of very standard, the simplest sort of set of database for tracking those transactions. So here's a sort of our current mock design of this process. So as you're writing code, you see that this line, in this particular case, I don't know whether you can see this or not, but what the red line highlights is a routine, a method call that eventually accesses one of those tables. Now, the assumption is, you work in an organization with an SSG. I'm assuming people know about BSIM and SSGs, right? So your security auditor says these tables are really critical. Access control, needs to be applied to those tables, let's say, for example. All right? So what we do is we say, okay, this call is going to have access to one of those tables. And we're just asking the developer at that time and say, where is your access control logic? Show me where is your access control logic. So the developer maybe at this point scroll up to this green line and says, okay, here's my access control logic. And that's what I mean by interactive annotation, which is you are relating different parts of the code. Here's a part of the code that does database access, and here's a part of the code that does access control check. And from a program perspective, we have no idea where the logic is, but the developer knows what it is, right? Hopefully. So what we're trying to do is inside IDE to bring out those relationships and capture them, right? And so two questions immediately comes up is where to ask questions, because there's so many different places you can ask the questions. And second is, what is a valid validation? So this is our current answer based on that. We think that ask the question at the level of database access, like SQL statements, is probably too low level, because you can have library routines that are called by different threads, right? Different transactions, and it may be two different levels. So the right level in our judgment right now is at what use case level, at transaction level. So you let's say you're in a web application, then this is what the user sees at the high level is transaction. So for example, it could be a Java servlet or some kind of an action, any kind of an MVC framework. You have this controller, high level controller that comes in. That's where you want to ask the question. So that's the first point. The second point is, what is a valid annotation? And sort of theoretically, what this annotation is really about parts of an invariant, a security invariant. So it's fundamentally a logic test. It's got to be some sort of a Boolean test. So okay, it's a Boolean test. Or in a different syntax, for example, something like Spring Security, it might be an assertion, but the assertion is really implemented as a logic test anyway. So fundamentally, it's a logic test. So that's first thing is it has to be a logic test, and it must be on the execution path from the web entry to your database access. So somebody just sort of clicks something randomly, we at least do some sanity check to see if the check, if your annotation is actually going to do anything for your for this critical path. Okay. Now, armed with that information, we can actually do some very interesting analysis based on that, and I think those kinds of analysis are not currently being done, at least out of the box in static analysis. So for example, here's your web entry, and here's your database access, and we ask the developer, where's your access control object, using this as an example. So this wiggly thing here is where the logic test that the developer says, here, this is where I did my access control. Now, we actually have no idea whether this is accurate, is sufficient. I mean, we're not getting that, all right? We just say, okay, looks like it's a Boolean test. It's on the path from the entry to the database access point, so we think it's, I assume you did a good job. But then we can do some analysis, path analysis in the code. If we find that there's another path on which there is no annotation at all, then we can know for sure there's a broken access control, right? Because you told me this is where your access control point is, but I found another path that you could get to the data. So we can do some, certainly these are not complete, but they are sufficient. Where we find is probably bugs, but we cannot find everything, obviously, okay? This is another interesting case. I'll give you an example later on. That let's just suppose you have two different transactions, two different use cases, and you ask the developer, and they may be written by two different people or different teams, and you ask for annotation. They all access the same data table, but they have different annotations. Now, I think it's really interesting to point out, at least to the development team, there's some discrepancy. Is this really true? Maybe one of them should be, extra check should be done, or what, right? So that's another example, and actually have a concrete example to show you that one as well. So how is that going to really work in practice? So we apply this technique to two open source projects, Rolla, which is the one we did analysis on. We also apply this on Moodle, which is a PHP-based course management system, which is phenomenally popular in the university community. And so we did that, and we used statistics, your bug track, security patches from those open source projects, and we found that in Rolla there were 6 reported security patches. 3 of them are sort of the input validation, output filtering type, which all can be handled by Aside as is in the prototype implementation. There is 1 broken authentication that can be caught by this annotation approach, and I'll give you the details. Moodle has 14 security patches. 1 of them is in the validation and encoding space. 2 of them are CSRF, right? And that could be caught by code annotation. And I'll give you these examples in detail, so hopefully you can see how this might work. So this is our reconstructed logic flowchart for a use case in Apache Rolla. So you have a web entry point and say, well, are the web headers valid? Right? If it's yes, you retrieve the credentials. Are the credentials valid? And if it's yes, you let it access the database, and if not, you throw an exception. But there is also a path where it says if the header is no, somehow it wiggles through the code and have access to the database. I'm sure things like that happen. We've seen this in the wild. And so what we would have done is we would have, here's the do-get method in which leads to the database access point, and according to our rule, we would ask a question of line 52, because this routine, this method call, eventually accesses the database, right? And then the developer will be, in this case, suppose that, following the logic, there were actually two checks for user ID and password that says, this is my access control logic, right? So they can annotate that here in this part of the code. But what we found was, through this analysis, that there's another path from the entry point to the database, so we can produce a warning as to this is a potential broken access control problem. So similar idea can be applied to CSRF protection. So here's an example of changing an existing user's profile in Moodle. So Moodle is a very complicated role-based access control system, because you think about course management systems, you have TAs, you have professors, you have students, you have system administrators, people can post grades, and and it actually has to comply with FERPA and then privacy regulations. So this is a very complicated role-based access control model. So one of the things you do is have a user profile, right? So this is a classic CSRF attack against some professor's user profile. Let's say, for example, a student wants to change the grade. So what you do is, now we sort of cast this in from PHP to Java terms, because we don't have this written in PHP. So we sort of say, well, what we would have done if we had this in Java. So this is your PHP file, and then later on, this highlighted line is eventually wind up to call a routine that accesses the database, right? So we define the set of databases, and it changes the user profile. So the heuristic we would apply, the simple rule we would apply to deal with CSRF is, whenever a web form submission contains an operation to update some database, some state of the server, then we would ask for annotation on CSRF protection logic. Just a reminder. Hey, it looks like this web form is doing something to the state. Where is your CSRF protection logic? And the programmer is going to have to do something. In this case, probably we'll ask this question in line 72, and then we'll pop this question. Now, okay, there was somehow a slide missing here, but I'll just talk through it. What happens is, in the case of Moodle developers, they obviously knew CSRF protection really, really well. They have designed special routines and patterns to prevent CSRF, right? So this is a very mature open source project. But even that, in two cases, the developers forgot to add the CSRF protection routines in. So later on, they would have to issue security patches to patch them up. So we found those out. So these are real cases. So if we had, our theory is, if we had asked that question to the developer at that point, where's your CSRF protection logic? The developer said, oh, I forgot. So, here's what I put in. So that goes back to our theory is we're trying to use these warning as a way to help people to avoid obvious mistakes. So here's another one, delete a post, and same kind of a problem, that there was no CSRF protection at all. And this is what we call triangulation. This is another open source project. This was first reported at the security conference last year. That interestingly, what this paper was trying to do, this research was trying to do, is they're trying to take a source code of a web application and perform dynamic analysis to find out bugs, right? And then so what you need to do is you need to give it sort of normal use cases, and it'll find security invariants. It will hypothesize security invariants and see whether it does. And I think Professor Giovanni Vigner from UC Santa Barbara is the team that's doing that. I think he has a company is trying to build this tool as well. So I think this is being, I don't know exactly what the status of it, but I know he was at the last year's AppSec USA, so he was talking about this. Okay, so this is a case that he pointed out as using dynamic analysis by comparing two different transactions and find out that in one transaction here you have two invariants, In another transaction, you have 1, and then you can point out as a potential broken access control problem, all right, as a power of dynamic analysis. What we're saying is we could have done the same thing, at least in this case, with static analysis, but with a little bit of help from the user. So that's very interesting. So if the programmer, if indeed the overhead of annotation is fairly light and the programmers don't mind doing that, they can provide some input to us, to the development process, where we can actually find out these things without having to do dynamic analysis. We can do static analysis, which is, I thought it was, from a research perspective, extremely interesting. So I throw this thing in there. And we did sort of a very quick analysis of SAN's top 25 dangerous programming errors, and we say, okay, we've got these 2 approaches, interactive code refactoring and interactive annotation. What sort of things that we might be able to help? And so we identified things that, this might have some impact. I mean, it doesn't solve all problems in all cases, but at least in some aspect that one of these approaches could have helped. So let me just sort of quickly summarize what we see as the benefits for this approach. And I want to talk about it at 3 different levels. There's the students, because as we said at the very beginning, education is very important. Most universities don't train people enough in secure programming. So being in an academic institution, we care about training the next generation of programmers. So we want to look at students. We want to look at professional developers. And we also want to think a little bit in terms of the enterprise perspective. So for students, what we have found is code refactoring, code annotation really helps to shape awareness. If you say, like in our universities, in many universities, people teach Java and then use Eclipse as the IDE. If we put aside in there, and then students go through 4 years and they see these things, so at least they get input validation, output encoding right? I mean, among other things, okay? So we think this is gonna make a difference. The other thing is professors generally are very busy and they don't grade on code really for most part. I mean, some of you are teaching part-time, I'm sure, or even full-time, that we don't always grade the code, we just test if the code works, and if it works, okay, that's fine, right? We do some functional testing, let alone secure programming. So, but with these approaches, we can actually single out, generate a report to faculty and say, hey, this student, is the student paying attention to security, right? So there's some indication that we can train students better. For professional developers, again, the premise is a reminder of security programming practices. In the case of code refactoring, it can sort of do some of the grunt work for you. So let's say you want to do ISAPI and using anti-SAMI. And it's pretty complicated. I have to read the documentation, et cetera, et cetera. But with aside, anti-SAMI is right there because it's part of ISAPI. You just click on it, boom, it's there, right? So it reduces the workload of doing the right thing. For code annotation, we think that the hypothesis is, these advanced analysis can be very helpful in terms of detecting some more subtle errors. We think that enterprise also benefits. For example, you can push out standard libraries, right? As Jing has showed you, that our rules can be extended. So you can write your own rule sets. You can write your own libraries and install them in a plugin. So they want to make sure that everybody who touches code will do the same thing, right? And you can collect statistics, whether people are complying with it, and maybe there's good reason for not doing certain things, but if there are, then you want to find out what these are. Also, the code annotation, in addition to helping you with collecting, SDLC statistics, can aid in code review. So today, your code reviewers typically use your Fortify or something. You run this against Fortify, and but you really don't have the application context. So for example, you're accessing a database. Where is the access control logic? Where is the CSRF protection? You have to read the code to find out. I mean, unless you have the developer sitting right next to you, and if he or she remembers, 1 month afterwards that what he or she did with the code, it's very difficult to do. Whereas with the annotation, if you can open up the file and retrieve, say, oh, okay, here it is. So at least you have some way of doing more in-depth analysis for some really critical pieces of code. So we actually did some user studies, right? This is all, okay. what real people think about it. So we did a user study on 15 graduate students and 10 professional programmers. I don't really have time to go into the details, but overall, people generally notice the warnings. They like this approach, but it works really well with students. The developers are more skeptical. They're sort of burning their genes. They want to get the functionality first, so they don't always pay as much attention to it. And so it's a little bit more subtle with developers, but overall it's very positive. And then obviously, this is a prototype design. We need to improve that. So we talk about this more in the paper. So in way of conclusion, because I have about 3 minutes, so we've introduced two mechanisms: interactive code refactoring and annotation. We think it can be effective addition to the best practice SDLC, preventing some basic vulnerable code from being written, and also improve the efficiency of static analysis. What we're doing right now, one of the thread of the one fork of this project is we got a grant from National Science Foundation just to sort of use aside in university curriculum, particularly introduction to programming classes. So we're doing that, and then we will hopefully have some results to report next year. And obviously, improvements are needed to make it more useful for developers. So future work, UI design, we have to look at support frameworks. I think we have most of the work already there, but we have to think about there's some corner cases we still have to cover. Make a site appeal to the professional developers. That's why we're here talking to you all and get your input. And thank you very much. I want to acknowledge the National Science Foundation for giving us the funding to do this work. I want to thank Fortify for giving us an education license so that we can do the analysis and benchmark. And your input above all, it's just like a minute or so, we can take a couple of questions. And here's the link. All the papers are available, and you can take a look at that.